As part of repairing my HP computing counter, I am doing a number of tests of the calculator section to verify that all of those calculator functions are actually working. One of the tests I found was giving some odd results. We can enter a number, and I'll just type in 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and if we press the display X function, you'll see it comes up with 1.234567890 and a G for giga down here. So it's 1.234567889 by 10 to the 9th. What we're able to do is swap registers. This is in the X register at the moment, and I can change to the Z register, and the Z register actually is showing a minus sign there, but 0, and you can swap it back, and you can swap these back and forth very nicely. But if we have it displaying what originally was the contents of the Z register in the X register, and then say clear X, and this is one of the tests that HP recommend, and then we swap the registers again, the number is now negative. That's a bit strange. We're also having other issues with multiplying a negative and a positive number together, and depending on the order of those numbers, you will either get a negative result or a positive result, not a negative result regardless of the order of the multiplication. So I'm not sure whether that is the same issue as yet, but we're going to find out what's causing this problem. Separate to the Z register board, which holds the numeric data for the Z register, is the sign bit, and this board A23 holds the sign bits for the X, Y and Z registers. And in fact, in this image here, we've got at the top right hand corner, you can see IC4A, which is a JK latch, and that has pins 12 and 13, Q and Q bar outputs. 13 are shown as the sign Z bit. Now, this is where we first need to test. We'll get the crow set up and make some measurements here, because we can flip the bit via the keyboard and see whether we're getting anything sensible happening there. These two traces are supposed to be the outputs of a latch, which is the latch of the sign of the Z register. With the keyboard, I can enter a negative number. That's now gone into the X register. Now if I swap it with the Z register, instead of an actual logic level changing state, the lower trace has increased in amplitude, and we're talking close on 2 volts AC there at about 60 megahertz. So this latch is basically fried for whatever reason. It's just self-oscillating, and its outputs are not going anywhere near normal logic levels. So I'll have to pull that out and replace it. Okay, well, U4 is for the chop, and we'll just cut the pins out and remove a pin at a time to minimise any damage to the board. We've now got this board repaired, hopefully, so I shall put this back in the unit and we'll fire it up and see what happens. Okay, the board's back in and we'll just see whether this works. Well, we've got some digits on the display. Let's just try something here. Okay, and display, and we go, okay, and we've still got a minus sign there. So that's not fixed. I think though what we'll do next is just to put some probes back on that chip and just see whether we're getting the same sort of signals. Let's have a look at that. Okay, it's not so much of a dramatic change, but there has been a change. If I put this in now, you'll get, wait a minute, start again, clear, display, and then I'm not sure if there is so much of a dramatic change. After changing IC4 and seeing that there was some improvement but not much to the signal, we can now start to look at what the latch is connected to. And as you can see on the diagram there, Q13, the sign Z, has a designation on the right hand side of that saying NC, which means that there's no actual connection to that pin externally. So that's a good thing, because it means that that signal looks to be contained within this board. Also, the Q output, the pin 12, that's also contained within the board. And in fact, both Q and Q bar outputs go into these other logic gates here, IC7 on the left hand side, IC7A. You follow the lines, pin 12 of IC4 goes into IC7A, and also looks like, if we just scroll down here, IC21, and if we come back, pin 13 goes into IC7A, and also IC14, pin 9 of IC14. Now, IC21 and 14 both drive a latch, which then in turn drives the sign Y latch, and as we're not experiencing any issues with sign Y, I'm suspecting that these will be all right. And so, going back up, the sign X latch is the one that we're getting some odd results with. I suspect that IC7 from pin 13 is, and it'd be IC7A going into pin 4 in that chip, is the one that's actually now loading IC4, and we're not getting any sensible results out of it. What we'll do is change over this component. Okay, well, as we didn't get 100% success, but at least we got some improvement. But it looks like these outputs are either being loaded, or they look like they're being loaded by something else. So I went and had a look through the circuit, and the only ICs that are connected to this 7473 latch on the Z sign part of the latch, which are the two outputs, Q, which is Q is pin 12 I think, and Q bar is pin 13. I may have that around the wrong way, but whatever. So the only signals, these two outputs, only go into inputs in this chip, which is 7451, and two other chips which are 7454s, 21 and 14. 14's there, 21's there, two 7454s. So this chip is driving these three chips here. So this one's for the chop. Alright, we'll see how that board goes and see where we go from there. Let's fire it up and see what happens. And we'll just zoom in a bit. And if we put in some numbers, okay, so I shall just pan across a bit so you can see the G enunciator there. Well, we don't have a minus on the Z now. That's interesting. And if we go here and we go clear X, and then we go back here, and we're now not got a minus. So that was the issue. The next step will be to see if this was related. We had another problem. I'll just clear that. If we put in, and in fact what I'll do, I shall just get the sheet. I'll work from the Hewlett-Packard test sheet so that we can do exactly what they recommended. I'm just going to unfurl this thing. What it says is, we're 0, so we'll put 1 on the display. And yes, and display it. Yes. Then we'll enter 2 and press plus. 2 and press plus, and we get 3, which is what we've had all along. Now we press minus, and it will go to -1. Minusing 3 from 2, we get -1. Then we press multiply, because we have still got 3 in the Y register, and we now get -3, which is what we're supposed to. Before I was getting +3. Now, next step is we'll press divide, and this should produce a reciprocal of 3, but I'm doubtful whether it'll work. Okay, so we've still got an error. Now the divide function is still not working, but at least we've cleared this minus problem, and it's actually cleared it for both storing in the Z register and also for multiplication, because before the order of operation made it dependent on whether you got a negative value. So if you multiplied -1 with, say, 3, you would get 3, and if you multiplied 3 with -1, so the order was dependent, you would get -3. So now that is working, so at least we've made a step forward, and that was 2 ICs that caused that issue. Well, I started to have a look at the error caused by both the division function and the square root function. Initially I started looking at the signals that were generated by initiating those functions, and the signals I got on the DSO were quite clean, and in fact I recorded a few of the images which I may add into this video, but of little relevance because they were clean TTL signals, unlike the counter and the data selector that I replaced earlier in the day. Anyway, I wasn't having much luck there, so I thought, alright, what I'll do is I'll work backwards from the error light and see where I get to as far as signals go. I've traced back from board A33, which drives some of the lights on the front panel. That went back to board A19, which in turn went back to board A28, this one here. And I pulled it out, and apart from ICs and very little other components, a few diodes, a capacitor and a resistor, there's not much on the board except the ICs. So I had a quick look at it, and then I noticed that this resistor here, right here, and I'll zoom in a bit, and you can see in the bottom corner of the screen, if we will focus, and there we go, it's sort of focused. This resistor here was actually, the lead wire was sheared at the level of the circuit board, right at the joint, and this may have occurred when I was removing these boards originally because I had to actually use a pair of pliers. I don't have a proper extraction tool for these boards and they are quite difficult to remove. Anyway, I must have sliced this, so what I've done is I've just quickly cleaned out the hole, J-hooked a bit of tin copper wire onto what remained of the resistor lead wire, and it looks like the thing's working again. I'll just reset up and install the board and show you the display on the counter. Okay, with the board reinstalled, I just switch on the counter and up comes the display, and if we put in, let's say 144, display it and then do a square root, and it's 12 and no errors. Similarly, if we clear that, put in 144 again, display it, and this time we'll divide that by 2 and we use the divide function, and it's 72. So we're not getting any errors on the divide and on the square root function. I went through the whole sequence and I got right through to the end of the, well, virtually to the end of the test procedure that HP give. They say test for a large number minus a small number, and I entered the numbers that they recommend, 180 and then 179 with a prefix of milli, and then did a minus, and the number came out way off. So I thought, well, what's going on here? And I decided to just go back over all of the tests again because it just seemed a bit odd. But before I did that, I was playing around and I just put in the 180 and then swapped it. Well, first off, I just swapped it between the X, the Z and the X register, and that was fine. If I swap it between the Y and the X register, it comes to 80. So we've lost the leading one off the 180, and I thought, alright, let's go and test. We'll do the 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 display, and then swap that, and this is one of the other tests that they have. Now I did this I'll start again. I did this before and it worked perfectly. So this fault has obviously just developed. We've got that one. Now I put in 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. And if I do this with the Z register, sorry, just kicking the camera there. I've got to get this right. We do 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 display, and that's correct. And then if we were to swap this with Z register and then put in 2, 4, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, and then display, and then swap it back and forth between X and Z, that works perfectly. Now if I do the same thing and now I can I'll just get this right. If we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 display, swap that to Y and then go 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8 display, and then swap back, and we're getting some having swapped the Z and the Y register boards here. The fault on the Y register has now moved to the Z register, so it's pretty obvious that this board here, which is currently in the Z register slot, is giving us the fault. The one of the BCD representation of the number in all of those digits has failed. After going on a few minor red herrings, I think I've found the cause of this problem in the Y register board. When I looked at the circuit, there's a multiplexer at the input, and that the data was possibly being corrupted through as it goes through that multiplexer. The other alternative was that it was being corrupted through one of the counters. I was getting to the point where I came to a dead end on the multiplexer chip, because when I pulled it out of the faulty board and tested it externally, it worked perfectly. So I've done a number of other tests all relating to that. I can't find anything that really says to me here's the actual fault, so my thinking's going back to the counter, and I thought, how can I easily test for the counter? And yet again, the keyboard has proven an invaluable diagnostic tool. With the way I was testing it before, I was putting a number in and then swapping the registers, and so I was swapping the value to the register. So the whole lot of data got swapped, and I thought the digits are clocked in serially, so maybe if I put the Y register in the X register spot, as I'm typing the data in, the incorrect data should show up on the display, and in fact that's what's happened. So as you can see here, we've got 0. If I enter, say, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, you'll notice that as I first entered in this digit position here, the number is correct. I'll just clear that and show you again. So it's 1, 2, and in fact what's happened is this has shifted along, and the 1 has become a 0, and the 2 is displayed, then 2 is still being displayed, and we go to 4 now, and that 3 changes to a 2, and then we get a 5 and 6, and the 5 now changes to a 4, and so on. So as we're clocking this in down the line, the first or the second chip that's accepting data looks like possibly is the faulty one. So that's the area of investigation next. IC 12 is the first latch for data coming in, and then it gets transferred to IC 13, and then to IC 8, and if I go over here to IC 4, then 3, and then 7, 6, 2, 1, 5, 9, and finally 10. And we'll see whether we lose the 1 bit. What I've done here is I've used the 1, the change in state from low to high on the output of IC 12. We're triggering on that. So what that means is I progressively look for the outputs down the line, and I'll just keep doing a measurement between IC 12 and whichever the output of whichever appropriate IC is next in the chain, and we should then, for one key press, we should see a pulse occurring on the lower trace, but that pulse will then be separated in time by an additional microsecond for every position away from, say, counter IC13. So IC8 should be located here, and the next one should be located here, and so on. So that's the next test I'm going to do. Well, interestingly, the very next IC, IC8, the output is actually a runt pulse. We're only getting not even 2 volts going through. So either the output on that chip is faulty, or the next chip in the line, which is IC4, is loading it. So it's one or the other. Well, today finally some 74 LS 160 counter parallel load counters have arrived, and these are to replace the part that was in here. 2 here, even though they've got HP part numbers on them, are 74 160s. These darker NS branded chips, I can't remember the number now, but it was a low power TTL version of the same chip, and obviously Hewlett Packard used more of these chips in these register boards than the 160s, because these are truly 1/10 power of these. I don't know why in each board there are 2 of the 160s, and these low power ones are in the rest of the register board, and it's the same for all 3 registers. Okay, well, we've had success. The calculator now appears to work correctly, because before I could swap over to the Y register and then swap back, and then we would actually lose all of the bit 1 data in the whole counter, or in the whole display. And I've been right through section 10 of the keyboard checks, which pretty much exercises most of the computing section. It's come up with no errors at all. So at least we know now that that register issue was that particular U8 chip on the Y register board,